Hello, everybody. Welcome back. Today we are continuing with the water resources chapter, and specifically, I have an example about pumps. It's a little bit of a more complex problem. It has more steps, or it requires more steps, more things to calculate before you get to the end, but it's actually a good practice problem. So I hope you enjoy it. If you have any questions, please don't forget to leave your questions in the comments below or in the comment section below. Again, I will remind you quickly about the free resources that I have. Credential evaluation. It's a free guide, step-by-step guide that will help you go from zero to evaluating your education like a pro. So just click the link below and you'll be able to download it for free. Another thing that I have free for you is if you are just at the beginning of the journey and you're trying to get back on track and study for the FE exam, I have a starting point for you. I had the simply supported beams, shear moment diagram, examples and explanations, everything you need to just get started. Click the link below and it's a free PDF and it should help you get started. Now let's move on with our example about pumps. The pump shown in the figure below operates at efficiency of 85%. The suction line is 12 inches in diameter and 500 feet long. The discharge line is 8 inches in diameter and 2,200 feet long. In order to pump water at a discharge of 1,200 gallons per minute, what is the required power rating of the pump? Horsepower. Assume all pipes to be cast iron. Assume minor losses totaling 15 feet of head loss. Okay, so the problem is asking us to calculate the required power rating of the pump. I will go ahead at the FE handbook and I will write down pump. I just need the formula for the power of the pump. And if I write pump, it should direct me straight to what I'm looking for. Okay, almost there. Okay, so here is the pump brake power. So this is the brake power and pump power equation. Okay, so here I finally got to the formula. So this is the pump power equation. This is what the problem is asking us to calculate, this W here. Let's write it down and then discuss every single component of this equation. So I wrote this formula down and I want to discuss each component of this equation. So Q is volumetric flow, which looking at this, our problem, I believe we're giving the flow, pump water at the discharge of 1,200 gallons per minute. And we will have to transform that into cubic feet per second. So our Q equals to 1,200 gallons per minute, and we have to transform into cubic feet per second. So 1 minute equals to 60 seconds. And then from gallon to cubic feet, let's see what FE handbook has to offer us there. We have units. Go to the unit section and find the gallon on the right side, and it will tell us what we need to do to transform it into feet, cubical feet. So in order to transform from gallon to cubic feet, we have to multiply by 0.134. And why multiply? Because it says so right here at the top of this page, says multiply gallons by 0.134 to obtain cubic feet, right? And this is what we're going to do. This means we have to multiply 0.134. That means that 1 gallon equals to 0.134 cubic feet. And from here, This goes away, gallon goes away, and we're left with 1200 0.134 multiplied divided by 60, and we get 268 cubic feet per second. Great. And then the next is the gamma of water. Gamma water is given in the FE handbook, and I believe it should be given here as well, if I'm not. It's actually specified a few times throughout the handbook. Fluid mechanics, let's go here. Gamma water, specific weight, and specific weight of water equals to 62.4 pounds per cubic feet. So gamma water is 62.4 pounds per cubic feet. And now this H is the head loss. Let's go here again to our pump power equation. And the H is the head. The fluid has to be lifted. The problem states that there are minor losses totaling 15 feet. Also, what we know is that the water has to go from this elevation to this elevation, meaning that head, I will call it head 1, equals to, so let's call head 1 the 15 feet that we're given in the problem. And then head 2 is the 540 minus 320 equals to 220 feet. And these two are called the static head loss. And as we know, also there is also a head loss due to friction. This is the formula for head loss due to friction, and we have it equals to friction factor F, L over D, V is the velocity, V squared over 2G. Let's write this down and calculate head loss due to friction. Let's focus on calculating the velocity. So the velocity needs to be divided into a suction line and the discharge line. So here, this is our pump, and this part we have suction, and then on this side we have discharge. Suction, discharge. So we have to calculate velocity from this suction and then velocity due to discharge. What we know is that we can use the formula that flow equals to V times A. And from here, we can calculate the velocity. Let's go and calculate the areas for each pump line. So at the suction, we have a diameter of 12 inches, which means our area is going to be equal to pi, and we'll transform this into feet, 1 squared over 4. So here we have 314, we should do pi, 4 divided, I get 0.785, 0.785 feet squared. And then on this side, area on discharge equals to pi times, we have a diameter of 8 inches. 8 inches divided by 12, we get 0.67. 0.67 squared divided by 4. And the area at the discharge side, 0.35. So now that we know this, we can calculate velocity at the suction and velocity at the discharge. So velocity at the suction equals to the flow over area at suction, and this is discharge here. And we have 2.68 divided by 0.785. So we get 2.68, 0.785 divided, we get 3.414, and velocity, and this is feet per second, and velocity at discharge equals to Q over A at discharge, and this equals to same 268 divided by 0.35, and we have 766. Okay, and now we have the velocities. We need to calculate the friction factor, which is this over here. And in order to calculate the friction factor, we have to calculate a few things. Let me do this friction factor. And we are getting to this table over here, which tells us that in order to calculate the friction factor, we have to calculate the relative roughness and the Reynolds number. The Reynolds number equals to V times D over kinematic viscosity. And we know that the water is, go back here, kinematic viscosity of the water at 60 degrees Fahrenheit is given in this table here. So we have kinematic viscosity at 60 degrees is 1.21217 times 10 to minus 5 feet squared over second. And so we can calculate the Reynolds number. Let's go ahead and do that. And then we'll also calculate the relative roughness. So this suction in this case, because we're going to have to calculate Reynolds number suction and then Reynolds number discharge. We have two portions. So velocity at suction times diameter at suction over kinematic viscosity equals to, we have 3.414. Diameter of portion 1 is 12 inches, which is 1 foot over. And then the kinematic viscosity of water at 60 degrees Fahrenheit is 1.217 times 10 to minus 5 equals, get 2.8 times 10 to 5. Now let's calculate the relative roughness of suction line, which we have to calculate in order to get the friction factor. This is this part, relative roughness of the suction line. Let's go ahead and do that. Epsilon over the diameter in suction And also we have to calculate epsilon over diameter in discharge. For this particular problem, let's get this epsilon. It's given in the FE handbook, right after this table, and for cast iron is giving in between 0.0006 and 0.003. For this particular problem, we'll take it 0.00085. So here we're going to have 0.085 over 1 foot. And here we're going to have 0.00085 over 0.667 feet. Let's see what do we get in both these situations. Here I have 0.0085, and at the bottom I get 0.00128. And now with these values, so let's think of suction. We have to calculate the friction factor for suction and then friction factor for discharge. We have the Reynolds number in suction, and we have not calculated the Reynolds number in discharge, haven't we? Yes, we have not. I think I just forgot. So let's calculate the Reynolds number in discharge, which is going to be V discharge times diameter times kinematic viscosity. So we're going to have 7.66 times diameter, which is 0.667 feet over 1.217 times 10 to minus 5. And this is going to be equal to 6.4 times 10 to 5. So let me just write it here. So for suction, I have Reynolds number as 2.8 times 10 to 5. And for discharge, I have 6.4 times 10 to 5. And relative roughness for suction, I have it as 0.00085. And for discharge, I have 0.00128. Okay, so let's apply that. So first for suction, 2.8 times 10 to 5. This is 10 to 5 over here. So we have 2.8. This is 2. Here, this is 2. This is 3. So 2.8, it's somewhere close to here. So I will try and draw a line. And then 0.0085, it's over here. So I will, so slightly going upward than this line. We can go ahead and assume that friction factor is very close to 0.02. So this line was here. And then 0.085, very close to this line. I can assume friction factor equals to very close to 0.02. Now, for discharge, we have 6.4 times 10 to 5, which gets me here. This is 6, this is 7, this is 8. So 6.4 is somewhere in between these two lines, a little bit less than a half. Just do this line like that. And then the relative roughness is 0.00128. 0.00128. So slightly, I will just go ahead and assume it's this line over here. And going all the way, it gets me to friction factor 0.02. So for both cases, suction and discharge, I will go ahead and use friction factor as 0.02. Let's see what is our head loss due to friction. So we have 0.02 L. Our L for suction is 500 feet times, we have 500 feet over a diameter of 12 inches, 1 foot, times velocity in suction, we have calculated here is 3.414 feet per second, over 2 ng, gravity acceleration, equals to 32.2. Let's go to FE handbook. Let's say you don't know how much gravity acceleration is. Let's go to units and page down. Let's go one more page down. And here we have in metric and US units, and gravity here is 32.174, and we round it up to 32.2. And plus, we have to add the discharge head loss, which is going to be 0.02 times L at the discharge is 2,200 feet over 8 inches in diameter, which is 0.667 feet, times velocity in discharge is 7.66. We'll not add the units because it's too messy. Times 2 times 32.2 equals. Let's go ahead and calculate that. See how much do we get. 7.66 squared, 2,200 multiplied 0.02 multiplied, enter 0.667, enter 2 multiplied 32.2 multiplied, and then plus. I get for 61.9 feet, which can be also rounded up to 62. So this 62 feet is the head loss due to friction. And if we go back to the formulas, this is the head loss due to friction here, 62.2 feet, which means that our total age in here, age total, equals to age 1 plus age 2 plus age F. And we have 15 feet plus 220 feet plus 62 actually. I don't know why I wrote this, because it's 61.9 and I rounded up to 62. So it's 62 equals 297. So our total head loss due to static head loss, friction head loss is 297 feet. And now calculating the power of the pump. I'm not sure, have we discussed about the eta total of this member here? This member here, if we go back, this eta here is total efficiency. Okay, so at the beginning of the problem is stating the pump shown in the figure below operates at efficiency of 85%. So this is our efficiency is 0.85. Now let's go back and calculate our power rating of the pump. Q, which is 268 times gamma water, which is 62.4 times 62.4 times the total head loss, which we just have calculated as 297 over the pump efficiency, 0.85, equals, we have 58,432.8, and this is pounds times feet per second. And remember, the problem actually is asking us the power rating of the pump in horsepower. And I want to go here to the units to see how much is the horsepower, because I don't know. So let's see, horsepower. So if you want to obtain from horsepower feet times pounds per second, we have to multiply by 550. Now, in order to get horsepower from feet pound per second, we have to divide by 550. So let me divide this number, 550. So I get 106.24 horsepower. And let's see our answers here. 106, and our answer is A. This problem required a little bit more work. I hope it made sense. If you have any questions, please don't hesitate to ask. That's it for today. I hope you found this video helpful. As always, I will ask you to subscribe and like the video if you found this helpful, because this helps people just like you find me. Keep up the good work on practicing the FE problems, and I will see you next week.